Good afternoon, and welcome to the very first inaugural Midwest Distinguished Aerospace Lecture Series. This series is something that was started this year as at the initiative of Philippe, sitting over here, and his counterparts at Purdue, Notre Dame, and the University of Michigan. This is a new format that we expect to continue for a long time, where a very distinguished speaker is making 4 pit stops in 1 week within the Midwest, starting with us, continue on to Purdue, then Notre Dame, then Michigan. So this is definitely quite a feat for the speaker, and so we're so grateful to Professor Yang to having accepted to do this. Just to say one word more about the lecture series, just to mention that this is a format where all 4 schools have a say. There was actually a committee put together by the 4 schools, and everybody, all the faculty got to vote, and we're very fortunate this year to definitely have been able to get our first choice on top of it. So this is somebody who is not only extremely distinguished, but somebody that faculty at 4 schools are very excited to hear from. So we're definitely very happy about this. And just to say a big thank you to the staff who helped put this together, because putting one seminar together is already quite a lot of work. You can imagine all the logistics that went into putting 4 together. So thank you so much to Deborah sitting in the back, as well as to Stacy, who helped us put this together. And without further ado, I'm just going to let Professor Dan Bodoni introduce our distinguished speaker for today. Thank you.
This is more than a laser pointer. Okay, so it is my distinct pleasure to welcome Professor Vigor Yang from Georgia Tech's Aerospace Engineering and Industrial Systems Engineering departments to our lectureship series. Professor Yang has been selected because he is a luminary in his chosen field, having started at Caltech with a PhD in 1984 in mechanical engineering under Fred Kulik. And since then, he has impacted several different organizations, technical fields, and academic areas. He's published 10 comprehensive volumes and innumerable, I'll add that, technical papers on combustion, propulsion, and energetics, a field in which he helped start as a student. He's the recipient of the AIAA, which stands for American Institute of Aeronautics and Astronautics Air Breathing Propulsion Award in 2005, the Propellant and Combustion Award in 2009, and the Von Karman Lectureship and Astronautics Award in 2016. In 2014, Professor Yang was awarded the Lifetime Achievement Award by the joint U.S. Army, Navy, NASA, and Air Force Interagency Propulsion Committee. That group is otherwise known as JANF. And he served as editor-in-chief of the AIAA Journal of Propulsion and Power from 2001 to 2009, and the JANF Journal of Propulsion and Energetics from 2009 to 2012. Among his many honors, Professor Yang is a member of the U.S. National Academy of Engineering, and is a fellow of the AIAA, the ASME, the Royal Aeronautical Society, and the Combustion Institute, and just recently stepped down as chair of the Aerospace Engineering Department at Georgia Tech in Atlanta. So it is with great pleasure that I invite Professor Yang up to the podium to please give our first Midwest Distinguished Lectureship. Please welcome Professor Yang. And the elephant in the room is this orange bag.
Yes.
We always embarrass our guests with gifts. And to honor your visit to the Midwest, this is a photograph compendium by a local author, Larry Canfer, on photographs representative of where we are.
Fantastic.
I give it to you with honor, and inside is a signed letter from our head, Greg Elliott.
Thank you so much.
Itself is worth a lot.
Thank you. Well, thank you, Dan, for this wonderful introduction. I couldn't be more grateful to the friends and the colleagues here. It's a tremendous honor to give the lecture today. When I received the bag from Dan, I thought Dan would first present to me an empty bag. Then depending on my lecture, he may put the gift into this bag. Yes. Thank you. Also thanks to Cedric for the tremendous effort. As you mentioned, to organize one lecture by itself is a tremendous effort, let alone 4 lectures within a week. Thank you once again. And Stacy, thank you so much. I just couldn't be more grateful to you. What I'd like to do for the next 45 or 50 minutes is to share some of my perspectives on high-fidelity engineering design innovation for aerospace systems. That's what I like to do, yes. Let me start with human space exploration and transportation. Human space exploration commenced in 1957 when Russia put the first satellite in space. Then in the past 70 years, tremendous progress has been made. For example, ICBM in the 50s and early 60s, and in 1969, Apollo program, that's essentially we were able to put 12 men on the moon. Then 1981, when I was a grad student at Caltech, space shuttle program started all the way through 2011. Within 30 years time period, there were 135 flight missions under that program. Then lately, everybody is so excited about Mars exploration. So that's a tremendous progress made in the 70 years. But what about a propulsion system? From the propulsion perspective, in the past 70 years, there were 32 major rocket engines established within the United States. The number is not that big, but every single engine that we established in the past 70 years was a tremendous accomplishment, yes. Here is a very typical example. The picture showing here is the Saturn V launch vehicle that we used in the Apollo program. When we look at the first stage, there are 5 F1 engines. Each engine produces a thrust somewhere around 1.5 million. That's equivalent to 6 Boeing 747 liftoff thrust. So that shows the magnitude. Well, for the entire Apollo program, the nation developed 6 different kinds of engines, starting with the F1 engine, that's a very mighty engine, then all the way to reaction control engines. For example, that thrust level is about 100 pound force. And this one shows the range of thrust of those 6 engines that we established in the 1960s. Yeah. But then the question is this: how much money that we spend on developing those engines and how much time? Here I'd like to share a few data points with you. The entire Apollo program, during that 10 years time period, NASA's budget was about 6% of the nation's GDP. And for rocket engine development, essentially, we do not know how much money we spend on that. But out of my personal curiosity, I personally invested almost 2 years' time to find out the money that we spend on the development of F1 engine. This is my number. Well, the background is the spreadsheet. Probably you noticed that I personally went through, to your surprise, almost several hundred pages of spreadsheets in order to get this number. Well, for F1 engine, the nation spent $2.4 billion, but that's 1966 money. That's equivalent to $18.72 billion in today's money. What about the upper stage engine, J2, the second stage? The second stage engine burns liquid oxygen and hydrogen. That engine, we spent $1.7 billion. And again, that's 1966 money. That's equivalent to $13.26 billion in today's money. So that's the money that we spent on developing those engines. What about a space shuttle? Well, space shuttle essentially was the product of the 1970s and the 1980s. For the space shuttle main engines, there are 3 shuttle main engines down here. Yes, there are 3, 1, 2, 3. And then the next question is how much money that we spend on the development of a space shuttle engine. Well, that's a $2.45 billion in 1980. And that's equivalent to $7.5 billion in today's money. So keep in mind those big numbers. But what about the future? Well, we still need rocket engines, but these days we are talking about 3 different kinds of missions. First one, of course, we are still interested in the LEO missions, right? But near the Earth, that's essentially commercial and military flights, basically. Then the next thing is we want to go back to the moon. Going back to the moon, we are talking about several hundreds of thousands miles. Then, of course, in the future, probably 10 or 20 years from now, we are able to send people to the Mars. Then we are talking about a long distance. But no matter what we do, we still need rocket engines. So the question is this: how much money that we should spend on developing our next generation engines? There was a huge debate about 5 years ago in Washington, D.C., because the issue was, should we develop our next generation engine? And if the answer is yes, how much money that we should spend on that, and how much time we are able to afford? I was engaged in that very serious and, frankly speaking, very heated discussions. I was asked by a senior colleague in DC. He basically asked me how much money that we should spend. Well, I try to avoid that question because it's a very political question. But at the end of the day, they put me to a corner. They say, you must give us a suggestion. Yes, I said, well, looking back, 50 years ago, the nation spent $2 billion. That's 1966 money. Then 30 years ago, in the 80s, another $2 billion. So if you ask me, my estimate based on historical number, another $2 billion, all right? What about time? Time is anywhere between 5 to 10 years. Now the question is this. This is something very interesting. Can the nation still afford the $2 billion? Can the nation still afford a 5 to 10 years time to develop the next generation rocket engine? The answer is no, we do not have money, we do not have time. So, that's one aspect. The second aspect is, then tell me, what's the number? So I made a very bold response to that question. I said, the nation should not spend more than $1 billion to develop our next generation rocket engine. Time-wise, should no more than 4 years. If we spend more than 4 years, and if we spend more than $1 billion, that means the entire space rocket propulsion business has no future. The reason is, this industry hasn't got a chance to incorporate recent and projected advances in other areas. For example, design, for example, advanced manufacturing, for example, materials. So in other words, if the nation cannot accomplish that within $1 billion, within 4 years, my suggestion is just don't do it. Why not we wipe out that industry, then we use our money to do something else. So that's my advice to the government at the time. Then the next thing is this: if it's $1 billion, so tell me, if you are a decision maker in DC, then you say $1 billion. The next question is, how would you like to spend your money? How would you like to spend money? Well, let's go back to the history. This one shows the cost versus the development year. In the past, we spent 2% of the entire budget on initial design. Engineering, from day one all the way to the completion of the program, that's about 10%. No, that's about 15%. And then most of the money was spent on testing, trial and error. If one design didn't work, then let's redesign, then let's retest it, the situation. And then the remaining part is 10% for system integration and demonstration. So the issue is this: is this a good business model? If the answer is no, then what should be a good business model? And then, then I also share, with the people some historical data. Taking F1 engine in the Apollo program as an example, that's the money that we spent. The number of tests for single engine certification, almost 2,000, more than 2,000 full engine test firing. That means, and redesign, rework means redesign, retest, and so forth. That number is 203 times. That means, each rework cycle cost us $9 million at that time. That's equivalent to $90 million in today's money. So that means, okay, if the initial design is not very close to the final design, and we have to redesign and retest, each rework cycle would take us 70 million. Who can afford? Of course, nobody can afford. Then that goes back to then the next one. Well, the next one is, well, we want to substantially reduce the time duration for engine development, and also we want to substantially reduce the cost. So from the chart over there down to this one, all right? Then if this is the case, the next question is, how should we do the business? Well, this is what I proposed, yes. We should make a major investment in the early stage. So in other words, initial design probably should take 15% of the entire budget, to the extent the initial design is very close to the final design. So by doing that, we can substantially reduce the resource required for testing and elimination of a failure. So this is a new business model. Well, conceptually, okay, this is very nice. Everybody would love to see this chart. If you can make your initial design very close to the final design, everybody would agree with you. But scientifically, technologically, and engineering-wise, how to accomplish that? That's a big issue these days. So, well, here, okay, I'd like to give you a simple example, still using rocket engine development as a case study. Then we see how we can proceed then to make major changes, and also at the same time to substantially elevate our technology basis. Well, what we're looking at is the most advanced rocket engine ever produced in the history. This is a Russian-made engine, which is called RD-170. RD-170 produces a 1.75 million pound force. It's even bigger than our F1 engine, but that's one aspect. The second aspect is this engine is so much more efficient than American-made rocket engine. It's about 10% more efficient in terms of ISP, which means a specific impulse and so forth. Well, if we focus on the combustion system, propellants burned in two stages, one in the pre-burner, the second one in the main chamber, all right? In the main chamber. Pressure is very high. Pre-burner pressure is well above 7,000 psi. 7,000 psi. Well, for comparison, aircraft gas turbine engine operates at a pressure anywhere between 100 to 300 or 400 psi, right? And the main combustion chamber pressure well exceeds 3,000 psi. So very, very high pressure device. So, and this one shows the design of this main combustor. Well, there are 331 injectors here. Gaseous oxygen, high temperature gaseous oxygen is delivered into this combustor through these 331 injectors. And at the same time, liquid kerosene is injected tangentially into those injectors. Combustion occurs in the downstream region shown down here. So I have to say, this is a rather complex system. And physical dimension is not too big. Physical dimension is about that big. Can you imagine that? For such a limited physical space, the device is able to produce such a huge thrust, sufficient to lift two Boeing 747 aircrafts. So that's the scale of the energy, yes. Then this one shows another view of the combustor, and this one, yes. So now we want to develop such a high-performance combustor. Question is, okay, how should we proceed in order to save money and also in order to make sure everything can be done in time? Well, first thing is this. What is the purpose of this design? The purpose of this design, of course, is to make sure this combustor is a high performance, almost 100% efficiency, combustion efficiency, and also everything is very stable. There's no unnecessary unsteady motions within this combustion chamber. If that's the purpose, then the next thing is we have to develop our design strategy. What is our design strategy? Well, the design strategy is number one, whatever injectors we develop must be 100% stable by requirement. Then we use internal viscous damping to provide the design margin, all right? If that design margin is not sufficient, then the third line of a defense is we want to utilize the acoustic damping provided by the flow distributor. If those three lines cannot provide us with a sufficient design margin, then the final result is we want to use acoustic cavity. Conceptually, okay, we consider this is so obvious, right? Everybody probably would do the same thing. But I have to tell you this. This was not a design practice used in the US in the past 60 years. In the past 60 years, whenever we develop a rocket engine, the first thing is, injector, we do our best to make sure it's 100% stable, but we're not quite sure whether it's 100% stable or not. So let's assume this part is 90% stable. Then we want to utilize the internal viscous damping and other devices to provide the design margin to make sure it's 100% safe. And I have to say that kind of a design strategy must retire. In today's environment, we have to be very bold to make sure this one is 100% stable. So the issue is, design strategy must be established upfront. Otherwise, we may not be able to accomplish what we really want to do. Then the next thing is, every system must be regarded as a dynamical system. Because it's a dynamical system, we need a mathematical model to characterize and describe the dynamical behavior of a combustion chamber. In this case, what we did is we developed a wave equation and with many source terms on the right-hand side. Then we use this equation to characterize the dynamical behavior of this combustion chamber. So conceptually, we may want to consider this a very high-level model and so forth. But I have to say that it's easy to write this equation. What about those source terms? That's number one. And number two is how to solve this equation. And especially with a complex geometry, especially with a very complex inlet and outlet boundary conditions. So those are the practical issues that we have to address. That's another thing. So then another thing is this. When we look at that system equation, which essentially is a wave equation, as I already mentioned, there are many source terms. So how to describe those source terms? Well, in that regard, we have to go back to the injector because combustion occurs in connection with each single injector within this device. Well, this is the injector that people used for this particular case. And this one shows more detailed design. Essentially, what we're looking at here is gaseous oxygen is delivered into this injector, and the kerosene fuel is injected tangentially through the outer annulus. Then combustion occurs down here. When we look at this geometry, then the next thing that we have to ask is how many design parameters associated with this generic design. Essentially, there are 12 parameters. For example, the length, the diameter, and the inlet confinement, and also location and the size of kerosene fuel injection. So there are 12 design parameters for this case. And that's number one. And the number two is, what may be the most appropriate range of each design parameter? Taking this RD-170 rocket engine as an example, the length of this injector is on the order of 10 millimeter. But combustion occurs down here, and the physical domain that determines the combustion behavior is very, very small, on the order of 0.5 millimeter. So in other words, if we do not understand the combustion behavior within that very small spatial domain, or if we do not know how to control the dynamics within that very special domain, then the chance to make a stable rocket engine is almost Tom Cruise, Mission Impossible. So that's the challenge that we are facing these days. Well, and what about the physics? Before we discuss the design, then what about the physics? Well, here I want to share with you 3 different cases. Case 2, down here, we have the center tube protruding into this area, yes? And then this case, okay, the protrusion always goes to the entrance of this taper region, all right? The first case, there's no protrusion at all. There's no protrusion at all. So from the design aspect, we have to ask ourselves, there are 12 design parameters. For such a design, if we put this device on the test stand, if something goes wrong, which design parameter that we should change? That's question number 1. Question number 2 is, if we have to change the parameter, the design parameter, how much should we change? So those are the issues. In the past, okay, those issues could only be answered through test firing, so-called trial and error. But these days, okay, we must be able to answer those very basic questions up front in the initial design stage. Well, here I just want to share several things with you. When we look at, okay, those 3 different designs, well, what is the design requirement? The design requirement is, number 1, we want to make sure the flame is very stable. The flame is firmly anchored in this region. That's number 1. Number 2 is we want to make sure the hardware can survive in such a high temperature environment. What is the temperature down here? It's not very high. For most, okay, for you, that's not a high temperature. But for most of us, it's a very high temperature, almost 4,000 Kelvin. So we have to make sure this device can survive, right? So, well, that's why, okay, everything must be high fidelity. Everything must be high fidelity in order to make sure we have a fully understanding of the situation. Yes. The next one shows some movies about the flame evolution. The flame evolution down here. Yes, and as you can tell, yes, the protrusion, the length of the protrusion of this very small piece of a component determines the entire combustion dynamics. So this is pretty much the situation. And one more time, the physical length of this inner tube is around 0.5 millimeter. And this is the case, yes. But then, okay, another thing, yes. Oops, the file is a little bit too big, yes. Oh, sorry. Yeah. Well, as I mentioned, okay, that's for the injector design, yes. Then the next thing is this. Well, we can do high fidelity simulation or modeling and simulation for a given design, But then the next thing is, okay, whether or not, is that the best design we can possibly have? And what is the best way to survey the entire design space? Because we have 12 design parameters there. Well, to answer that question, okay, we have to utilize the most recent advances in data science. We have to use emulation. So the procedure is the following. We started with a conceptual design. Say this is my injector. There are 12 design parameters. For each design parameter, we provide a range of dimensions, all right? Then after that, okay, what we really want to do is we want to survey the entire design space. But with 12 parameters, to survey the design space using high-fidelity simulations, such as a large AD simulation, is not very practical because you just have way too many cases to do it. So the next thing is this. We have to apply DOE techniques, design of experiment techniques, to down-select the number of cases. Then after that, we do the so-called emulation. And here, okay, I want to share with you the procedure. And let's consider a very simple case. This one shows a very simple swirler. Liquid oxygen is delivered tangentially into this tube. And as a consequence of the centrifugal force, the liquid film is attached to the surface while convecting downstream. All right, this one. Well, for from the design perspective, okay, there are 5 design parameters. We have the length, we have the diameter, and also we have the size and the location of the fuel injection port. So 5 design parameters. For each design parameters, then let's assume we provide 10 choices, all right, 10 choices. Then the number of choices becomes 5 to the 10th power. That number is huge. That number is huge. Practically impossible. So we apply a statistical method, so-called design of experiments, to down select 30 cases. Hopefully, those 30 cases can represent the situation for the entire design space, all right? And there are a number of techniques that we can use. For example, we can use Max Pro or other kinds of design of experiment, design of experiments techniques to do it, yes. But for this particular case, we consider 30 design cases down here, right? Yes. And this one just shows the space filling of the techniques that we used. Yes. Oops. Yeah. All right. And this one shows, okay, the range of dimensions that we consider. We consider, okay, a very short but a much wider swirler, as shown down here, or we can consider a very long but much smaller injector down here, all right? And this one shows the parameter range. But in any case, okay, through the DOE process, we down select 30 cases, right? Then the next thing is this: what is the best way to describe the situation over such a design parameter space? The design parameter space, that's a real issue. That requires, okay, a technique. We call that emulation. Emulation. And well, emulation, okay, people call that, some people call that kriging, and some people say that's a part of machine learning or even artificial intelligence, depending on whatever you want to call. But the situation is this. We consider, okay, 30 cases. This is case 1. That's the injector. Then this is the downstream flow domain. And that's case 2 and case 25. So the technique that we used is called a common POD technique. In other words, okay, we map different geometries to a common geometry down here, all right? So in other words, we conducted large eddy simulation for each of those 30 cases. Then after that, we map the results to a common configuration shown down here. That's why the technique is called a common POD technique. Then once we have done that, yes, once we have done that, well, this one just shows the different domain, yes. Once we have done that, then we can quickly survey the entire design space. Very quickly, yes. Well, this one, oh, I'm sorry, yes. Yes. This one shows, okay, the emulation results. The upper half shows the large eddy simulation results. The lower part shows the emulation results. So essentially, okay, well, what we did here, as I mentioned already, we consider 30 cases covering a broad range of parameter ranges, all right? Then after 30 large eddy simulations of those 30 cases, we were able to obtain the training database. Then using the training database as the basis, we do the so-called surrogate modeling. But the surrogate modeling in our case is called emulation. And this one shows the emulation results. Well, for this particular case, the results are very, very encouraging. In terms of the accuracy, for example, the time evolution and also the different spectral information, the accuracy is almost 99%. But the good thing is this, to do large edge simulation, that may cost hundreds, thousands of hours minimum, CPU hours. But emulation, you probably can do it on your desktop computer in less than 1 hour. In less than 1 hour. So that means, in the future design, yes, once you have selected your design parameters, then after going through DOE techniques, you choose a much smaller number of cases for high fidelity simulations. In today's environment, it's a large edge simulations. Then once you have that database, then you can apply the most advanced data science techniques, so-called emulation, to help us survey the entire design space. Then the time saving between simulation and emulation is tremendous. For this particular case, I would say it's almost 10 to the 5th order, 5 orders of magnitude saving. That's the case. Well, that one, is a very simple injector. Then what about a more complex geometry, taking RD170 injector as an example, as shown down here? Well, for this case, for this case, the combustion case, the situation is much more complex, but we still do exactly the same thing to help us survey the design space. The simulation results is there, and our emulation results is shown downstairs. Yes, and this is the situation. Another thing that we have to be concerned with is this. Well, so far we only discuss simulation and emulation. What about important information such as a combustion response? Because all unsteady motions within a combustion chamber came from unsteady combustion. Come from unsteady combustion. Then this is another part of a data science which can help us in a tremendous way. Yes, in other words, using latest advances, not just the latest, but also projected advances in data science, we are able to identify the most important attributes to combustion response. So this is another important aspect that we may want to know. And another thing which I think is very important, although the emphasis here is a high fidelity simulation and data science, what about experiments? Well, experiments plays a very, very important role, yes, in this area, because for verification and validation purpose, yes. In that regard, we establish a very high pressure combustion rig, and this combustion rig is able to operate at a very high pressure, somewhere up to 2,500 psi. Yes, a very high pressure. Then we conducted this experiment at Air Force Research Laboratory. Air Force Research Laboratory provided us with air supply, the facility. Then we brought our combustion chamber to that facility to do the experiment, and then using that data to help us understand not just physics, but also to validate our numerical results. So this is another aspect. Yeah. I see Tong Hong here. Tong Hong probably is the very best combustion experimentalist in the nation, Tong Hong. This is yours, yes. All right. This one only shows the numerical results anchored by the experimental data. This is for the high fidelity part. And then, another thing that I want to mention is so far we only discuss the behavior of a single element injector. But for a practical system, a complex system, taking RD170 as an example, we have 331 injectors. So what is the best way for us to package those 331 injectors within a combustion chamber? Well, that's another very important design aspect that we must address. Well, to make the story short, we should be concerned with the spacing between each pair of injectors, between each pair of neighboring injectors, right? That's one. And also the arrangement is another issue. And the third issue is, should those 331 injectors have exactly the same dimension, or the dimensions should possibly vary by a very small amount? And that is a very, very important issue. In the old days, okay, there's no guideline, especially there's no quantitative guideline. But in today's environment, we can provide a very, very specific quantitative guideline as to what is the best way to determine the tolerance and also the arrangement. Talking about this, okay, I'd like to share, okay, a very simple example with you. What is the biggest nightmare for rocket engine designer? What is the biggest nightmare? Well, people would say, okay, the nightmare is I spend so much time and effort, I finish my design, but once I put my design on a test stand, it failed, right? Would you consider that your nightmare? Well, of course, okay, that's very depressing, but that's not your nightmare. Your real nightmare is you finish your design, all right? And your design passed certification, all kinds of testing. Then you use your design for flight engine. The first flight engines went extremely well, but the engine number 101 failed. You got crazy, right? The first 100 engines went extremely well, but engine 101 failed. Then what are you going to do, right? I would consider that our biggest nightmare. So the question is this: can we avoid that nightmare in the design stage? The answer is yes. Okay, we can do that. Yes, and again, we can well, in practice, okay, what we can do is among those 331 injectors, probably okay, we can divide those huge number of injectors into small number of groups. Then for each group of injectors, we vary the dimension slightly to the extent statistically it's a sort of a random distribution to bypass that question, all right? So there are ways to do it, yes. Then last thing that I want to share with you is a detailed numerical simulation for a cluster of injectors. And for this particular case, our concern is the spacing and also the parameter variation for those injectors, for those injectors. And this is another domain of our design space that we should be concerned with. Yes. And then once we have accomplished that, okay, then we should go back to our system level equation, because through the process that I just described to you, we are able to solve that wave equation. Then once we know all the source terms in that wave equation, collectively, we are able to characterize the behavior of this rocket engine combustion chamber. So that's how we solve this problem. Yes, from the design stage, yes. Well, to wrap up, okay, I have to say that, okay, we are already in a different stage in developing the next generation engineering products, especially for a complex system. Today, okay, I presented to you an example of a rocket engine, and the process, as I mentioned, okay, everything should be high fidelity based. Well, sometimes we heard, okay, for design, we may want to use a multi-fidelity approach in order to save time and efforts and so forth. But it's my personal opinion that we are already at a stage that we can do higher fidelity modeling and simulation, such as Dan's work and many others in the audience. If we can do high fidelity, why don't we just do high fidelity up front, right? And then, but that's not everything. After the high fidelity simulation, we must use new techniques in data science area. For this particular case, I mentioned emulation. That helps us survey the entire design space. And for large AD simulation, as I just mentioned, each case, several hundreds of thousands of hours is very typical. Probably that's only for a small case, yeah. But emulation, you really can do it on your desktop computer in less than 1 hour. That helps us survey the entire design space. Once we finish the survey of the design space, what's next? We can do optimization and uncertainty quantification. That helps us close the loop of the design. What is the final goal? The final goal, of course, is we want to make sure our initial design is very close to the final design. If we can do that, okay, I'm pretty sure those who are investing in rocket engine business, for example, Elon Musk and Jeff Bezos, they will be very happy. They'll be very happy. So trust me, okay. If people ask you, okay, how much money that we should spend on developing our next generation rockets, historical number, one more time, is $2 billion. But that time is gone. That time is gone, right? I would suggest $1 billion. And perhaps then you can further reduce the price down to $500 million. Make a huge suggestion to Elon Musk, and I'm pretty sure he will love you. Yes, yes, and thank you very much. And again, okay, and again, I have to say that, okay, we are now in a different time. Yes, if the business as usual, as we did in the past 70 years, that means this business has no future. Then the next question is, where's the future? From the design perspective, I think the future is based on the organic collaboration between engineering science and the data science. Then that's my humble opinion. Thanks very much.
Thank you very much, Vigor.
Sure, thank you.
And let's open the floor up for questions on the seminar. I mean, I only have to make Elon Musk happy. You guys can come up with a question.
Oh, you can make Jeff Bezos happy.
Go ahead, way in the back.
Sure, hi, thank you for your talk. So in the presentation, you went off of a reference or existing design to apply these techniques to kind of advance the rocket engine.
Yes.
How do you see data science feeding into like new or novel topologies that maybe we don't have a reference design for? How can we use these techniques to design new things?
Yes, if you want to come up with a totally different design for the same purpose, yes. Say for example, taking this rocket engine as a specific example, if you want to come up with a different architecture, sure, you can do it. But there's a risk down there. Keep in mind, yes, design a rocket engine, or I should say, design of a flight vehicle in today's environment is not something brand new. People have been doing that for years. So the issue is, okay, what is the best way to introduce innovation? And I think that's the key. That's the key, yes. Innovation may come from a totally new, different design, as you just mentioned, or innovation may come from the process. And today, okay, I only talk about the process. What is the best way to introduce innovation into the design process? Yes, and if you have different ideas, okay, for example, different architectures, I think that's much needed and welcome.
All right, another question?
Yes.
So you describe Thank you. You describe the cost versus time,
yes,
right? And showed that there's a potential for evolving from, spending 70-some% on testing and,
yes,
and changing the design down to, I think it was about 50%. Would a method like the one you describe here, would that allow to reduce this even further to
yes,
the point where you could spend only 20% of your time and therefore reduce the cost tremendously, because I assume that most of the cost is spent on the redesign and the testing of all these engines.
Yes, that is the goal. Yes, that is the goal.
Are there other examples of very complex technological achievements in which this kind of reduction has been achieved?
Reduction of the resource spent on testing, I would say, it will have to come from the design. Yes, as I mentioned, if it's a good design, then we can bypass a lot of unnecessary testing of bad designs. That's the whole purpose. That's why I propose, yes. Historically, whether it's aircraft engine or rocket engine, the initial design accounts for only 2% of the entire budget. Can you imagine that? Folks spend only 2% of the budget on the initial design. And that's not acceptable. But then the next question is, what is the right percentage for the initial design? To the extent the initial design is very close to the final design. That is a question to be answered. But here I propose a 15%, maybe 20%. But it's a 20% of substantially reduced the overall budget. It's not 20% of the original budget. So the saving is tremendous. And I think that time is coming. Talking about this, yes. Taking space transportation and exploration as an example, what limits our capability to do space propulsion? Say, for example, if you can afford $20 million, you can travel to space for 3 days. That's the market price. Who can afford $20 million? But we want to reduce that cost. Do you think $200,000 is a reasonable price for 3-day travel to space? I would consider probably then you can afford it when you retire. Yes, when you retire. Yes, and so the limiting factor for space activity, especially for LEO activity, is the price, is the cost. People talk about the cost all the time in the past 70 years, but there was no real progress in the past 70 years. And I think it's the time for us to make a change. For deep space exploration, the limiting factor is one, travel time is way too long. If you want to go to Mars, Philip, you have to invest almost 3 years' time. One-way trip could be anywhere between 150 days to 360 days, depending on the relative location between Mars and Earth. And once you arrive there, I'm sure you want to spend time looking around, right? Maybe 6 months, then another year to bring you back. So the propulsion system needs a fundamental revolution, basically. And all comes from here. All right?
All right,
Yes.
Jonas, go ahead.
So I think something that is important there is the arrow down to manufacturing.
Yes.
And in the 60s, design probably didn't take as a big part of the process because the realization was a big problem as well.
Yes.
So you might design something that has very fine features and they will not be able to be machined, or new machining processes might have to come about.
Yes.
What is it today? I'm going to throw in additive manufacturing, although it doesn't really apply to those temperatures yet. But what is it today that can actually facilitate the translation of those designs faster to real systems? Because I'm sure there's compromise in the process. And in the past, there was a rough design, but then it had to be translated to something passable, right?
Yes. Yes.
Now maybe it's a little bit easier, right? How have materials enabled more your ability to design something more precisely and realize it? New materials or new processes?
Materials for sure plays a very important role for very obvious reasons, yes. And then the next thing is manufacturing. 3D manufacturing has become a very important factor these days. Yes. Here I want to give you one example. Yes. And again, okay. Let's go back to a rocket engine. Yes. What is the cost of a rocket engine? By the way. What is the price tag of a aircraft engine these days? Well, the price tag, okay, well, the formula is very simple. For aircraft gas turbine engine, it's about $250 per pound force. Yes, all right? And for the rocket engine that I just mentioned here, probably the market price is 30 million. 30 million, yes. Now, and if we apply, okay, more advanced materials and manufacturing, we can substantially reduce the price. I'm talking about the practical aspect. I was told, if we apply 3D printing technique, in fact, it has been already demonstrated, probably, okay, they can reduce the price by 75%. 75%. It's a tremendous, yes. So that offers many opportunities in research, manufacturing, and materials. It's a very interesting business, basically. But I think, okay, here today I use a rocket engine as an example. The same thing applies practically to all the aerospace engineering products. Yes.
Do you have any estimate for SpaceX Raptor engine design total development cost, like you used to?
Oh, well, the question is, okay, do I have any knowledge about the development cost for SpaceX as a Raptor engine? Is that the question? Well, I don't know. It's a trade secret held by Elon Musk. Yeah, I really don't know. But I can tell you, he doesn't have that much money to invest if it's 1 billion. 1 billion, okay, you'll be very surprised, okay. 1 billion is a lot of money. The only person who can possibly afford is our friend Jeff. Right. Not Elon Musk. So short question to you is, the development cost of a Raptor engine must be substantially less than 1 billion. That's for sure.
All right, thank you very much. I think with that, we're out of time. Please let's thank Professor Yang.
Okay, well, thanks very much.